Hi guys, welcome to this presentation on feature selection methods. In the last video, we talked about one filter method. We'll continue from there, and we'll essentially talk about the covariances and what's the intuition behind covariances, why covariances are so important in data science and machine learning. Essentially, covariances are how the variables play together. So if the values in one variable increases or changes, similar change or in terms of direction, do we see similar changes in other variables? And association or associating the changes in one variable versus the other variable is called covariance. So let's look at fundamentally what it characterizes covariance. It's a measure of degree to which the two variables change together. That means either the direction of change would be the same in those two variables, or it could be opposite. So when the direction of change is same, is called positive covariance. That means one variable increases, the other one also increases, and if one variable decreases, then the other variable values also decrease. So that's called positive covariance. Negative covariance is when one variable increases, the other one is just opposite, it decreases. So that's called negative covariance. When there are no changes, for example, if one variable changes, the other one has no impact, then that's called zero covariance. So the covariance is simply a measure of magnitude, not in terms of normalized value, but simply a numerical value, the change in one variable multiplied by change in the other variable. Typically, we use the covariance in a normalized manner because simply a number, let's say 850 of covariance, really doesn't, tell much except the fact that it's positive. So we normalize it, and when we normalize the covariance, it gives you a correlation. So when you normalize, it reduces the value of covariance in the range of +1 to -1. So the types of covariance, the positive covariance means directionally the changes in the two variables are the same. For example, here, if the variable 1 and variable 2, so variable 1 is increasing in this direction, variable 2 is also increasing. So that's called positive covariance. Similarly, negative covariance would be just opposite of that. That means the change is in the opposite direction. Let's say the values are increasing, so this value is decreasing. So that's called negative covariance. And zero covariance is when there is no impact because of change in one variable on the other variables. So that will be randomly spread, so it doesn't tell you much in terms of linearity or in terms of direction, whether the change in variable x has a similar effect on the other variable. So calculating covariance is quite similar to what we have seen in the variances topic. So now with covariance, there is no such thing called minimum and maximum because these are simply scalar or real values. A covariance of 50 may be strong in one project, but may not be strong in other project. So it depends on the context and the domain. So typically what we do is, let's take a column X and then find out the mean of X. So let's say there are two columns here. So we find out the mean of both of these columns and then find the deviation of each of the point in X versus the mean. Similarly, each of the point in Y versus the mean, and then multiply. So you're going to multiply the deviation of each one of them. And after that, add them up, divide by the number of samples. So that's going to give you a measure or scalar value or a real value called covariance. So what are the use cases of this covariance? Now, as I mentioned, the covariance is very fundamental concept used in data science and machine learning. I'm going to show you the intuitive or geometric interpretation of covariance in a while. So the use case of covariance is in dimensionality reduction, like let's say we have 1,000 columns or 100,000 columns in a data set. Can we reduce it to a lower dimension without losing much information or data from the data set? Now, in order to get these dimensionality reduction algorithms to work, we use in the backend, we use covariance. Multivariate analysis also utilizes a lot of, the concept of covariance. For example, discriminant analysis, which is actually a topic for our discussion in feature extraction section. And you will see how the concept of covariance is used in discriminant analysis as well. Next, I'm going to show you the intuition that we can draw from the concept of covariance using Python code. Okay, so here's the little Python code for demonstrating the concept of covariance and also, getting the geometric sense of covariance. So again, I'm going to be showing you using some dummy data. Let's say there are variables x and y, some dummy values. First step, compute the mean of both x and y, and then compute the deviations for each of the points in x and also each of the point in y. Calculate the covariance, which is simply multiplication of both these deviations, and then apply the average, and that's going to give you the covariance. Now let's see the geometric interpretation of the covariance. So we will simulate uh, positive covariance, negative covariance, and zero. And the way we have taken this data is, intentionally to give you a sense of positive, negative, and a zero covariance. So the positive covariance is here. The value x is increasing on this side, but yeah, at the same time, the value y also increases on the same direction, means the positive. Here is the opposite. The value x is increasing, but the value y is decreasing. And here is pretty much random. There is no pattern in terms of direction. So that's called zero covariance. We will simulate all these three data points and then we'll see the intuition here. So the data set is here. This is a negative covariance. That means if you notice the values here, 18, 15, 11, and then the other column is showing increasing trend. The positive covariance means both of these columns will be increasing in this particular example. Zero covariance means just random value. So let's take, for example, the negative covariance, and then let's see what we see here. Okay, so we're going to simulate some data points, which is going to give you a negative covariance. So let's take the data, the negative covariance, and we're going to compute the mean of the first column, mean of the second column, and these are the mean. And then after that, we're going to save the mean in some data frame, like column x1 and x2, and this is the value here. And then we subtract the mean from the individual columns like x1, x2, and that is the deviation that you're seeing here. Okay, now what we're going to do is to multiply those two deviations, and that's in the another column in the data frame. Sum them up. That's going to give you the net covariance. Now let's plot this data points. For example, first one is just plot the data point and then draw the mean of column 1 and also the mean of column 2. Then after that, we're going to read every point and then show you here the rectangular area. For example, what this plot is doing is, these are my points, the black dots are my points. For example, let's take this point here, this point versus the mean. So the difference or the deviation of this point is nothing but the difference of the mean along this coordinate with this mean. Similarly, this point versus this particular line, which is a mean on the other side, and this is the difference here. So when you multiply these two, it's going to give you a rectangular area, and that's the area giving you a sense of covariance. Now, when you add all of these numbers, let's say the green ones, all these numbers which give you a green one, and that's positive, and similarly on the other side it gives you the negative here. So when you add them, all of these numbers, that's going to return you a net covariance here. So we let's simulate for the positive one, and then let's see what we get. Okay, now for the positive one, let's uncomment some of these lines here. So this is my positive. These are values which will give me a positive covariance. Now the same step here, follow the same step and then plot it here. Now you notice here your positive and negative, they will actually cancel out in this particular case, and net would be your positive covariance. Yeah, let's look at one more time. This is my positive. I think I made a mistake in the previous one. I just commented the last one here. So this is going to be a positive data, and then let's run all of these and let's see the, yeah, so now you see a positive covariance. That means the data is predominantly in this direction. Okay, and the geometric sense is the covariance is nothing but the area or bound by the differences here, right? So this is the area here, and now when you add all of these area, that gives you a net area in the two-dimensional space, and you can extend this idea to a 200 dimension space as well. So the covariance is nothing but an aggregation of space in the multidimensional space, and positive covariance will tend to be in one direction, and the negative covariance will be in the opposite direction. Zero covariance will be a random one. This is the intuition behind the covariance, and this idea of covariance is used quite significantly in many of the advanced feature extraction techniques like principal component analysis, then discriminant analysis, and so on and so forth. And in the next section, we will see how we extend this idea of covariance into correlation. Yeah, so that was a demo on the covariances and the intuition on the covariances here. In the next video, we'll talk about correlation, which is the next step, or how do we convert the covariances to correlation. See you in the next session.